Let's talk about IP addressing history. The reason why it's important to know the history of IP addressing is because by understanding the history, we understand certain components of IP version 4 and why IP version 6 is necessary. So this gives us some good insight into IP addresses and why they function the way they do right now. Now we could get really in depth into IP addressing and subnetting, but that's not the intention of this course. That's a whole nother course. So what we're going to be talking about in here is a real brief overview of the IP addressing history. We're going to talk about RFCs and what those are. Then we're going to get into the first iteration of IP version 4 and some of the real drawbacks to the first iteration of that. Then we'll talk about classful addresses and how classful addresses are set up and what they look like. We'll talk about where subnetting came about and what it looks like. Then we'll get into CIDR, VLSM, Classless Routing. Once again, it's not going to be an in-depth look into that. We're just going to be covering it real quickly, and then we'll take a look at private addresses, and then we'll wrap this up with IP version 6 and just a brief overview of IP version 6 and the need for IP version 6. So an RFC is a request for comment. The request for comment is put out by the Internet Engineering Task Force, or the IETF. So the IETF puts out these requests for comments. It's a way to get standards out there for public viewing, so that way anyone can go out there and see what these standards are when it comes to different internet protocol standards. And so they'll put this out there, and then that is what becomes the standard for everyone is supposed to follow those. So these are the RFCs. They're publications, and they sequentially work their way up. So, you know, the first publication would count up 1, 2, 3, 4. This publication right here is RFC 791. So you can see that right here on this. And in this example right here, it says it replaces RFC 760, so this is to take the place of that. And you can go and look these online, and they're really interesting. As you go through it, it helps define what internet protocol is and what IP addresses are and different standards amongst this. So it's very fascinating, but this is where we can dig in to find out where the history is and what the current standards are. So we can go out here and look at all the current standards. If we're equipment manufacturing, then we probably have to go and take a look at these to manufacture equipment according to this standard. So that is the RFC, or request for comment. So before we get into the different RFCs around IP addressing, let's first of all take a look at an IP address in itself. The IP address is 4 octets. Octet would be 8 bits, or that we also know that as a byte. And so in this example right here, we have 8 bits, 8 bits, 8 bits, and 8 bits. And of course, we don't put that into ones and zeros because we're not used to seeing ones and zeros. That's not what we typically work with. And so this is being shown in decimal format. And then we break up the different octets with just a period or a dot in between those. And so this example right here, we'll read this as 192.168.0.32, and that is the IP address and how we read the IP address. One of the first iterations of Internet Protocol version 4 was done in 1980. And it came out with a request for comment 760, an RFC 760. And RFC 760 defined a lot of internet protocol and IP addresses and how this communication happened and how we address certain computers or certain nodes on the network. And so this RFC 760, when it first came out, it specified this first octet of this represented the network. And so these were all of the networks right here. And the second part of this represented the hosts. And so when we looked at that first octet, we could identify what network this was a part of and route based off of that. And then the second part of this just represented within that network all the different hosts that were within that network. Now, the problem with this is that this is 8 bits, which gives us 256 possibilities. So what that equates to is there's 256 networks that this model can represent. And the number of hosts is quite large. And so when you're looking at 256 networks, that just is not enough networks. They didn't realize at that point in time how big these networks would grow, how many networks there would be. And as far as number of hosts, that number of hosts on a network becomes very unmanageable and very difficult to manage. So neither of these two elements was very functional. And so this RFC 760 that came out in 1980 was very short-lived. So to compensate for this, in 1981, they came out with an RFC 791. The RFC 791 was to address some of the shortfalls of that first iteration of IPv4 addresses. So they defined different classes. And the classes, what it needed to do was it needed to accommodate, number one, having a lot more networks, but it also needed to accommodate big networks that had lots of hosts. So they needed to develop a system that met both needs that the prior iteration did not do. And so what they did is they defined different classes. And they said if the first bit is 0, then we're going to define that as a class A. And a class A is going to be just like the original. The first octet is going to represent the network side of the address. The last 3 octets will represent the host side of this. And so this will be the networks, this will be the hosts. These are for very large networks. All right, so that's class A. For class B, it's going to start out with a 1, 0. The first 2 bits will be a 1, 0. This will be a class B. If it is a class B, then what we're going to say is the first 2 octets represent the number of networks there are, and the second 2 octets will represent the hosts. So this is the network side of the address, and this is the host side of the address. All right, so that's a class B. And then we have a class C. A class C starts out with 1, 1, 0. And what that does with a class C is that the first 3 octets represent the number of networks, and the last represents the host. So this is the network side of things and represents the networks, and this side represents the hosts on that network. So that's classful addressing, and classful addressing was a way to break apart this IP space into big chunks, medium-sized chunks, and small chunks to better accommodate for businesses and networks that were popping up all over the place. So let's break down this classful addressing. I could go really in depth into breaking out how we come up with all of these numbers, but that's a topic for another class. And so really, I just want to hit this from a very high level. Now, here are the different classes that are out there. There's a class A through C is the ones that we're mainly concerned with. There are a few more others, but we're not going to really tackle that too much within this class. Just know that there are others. Here I've got class D and E represented with a multicast cast in the experimental ranges. But let's focus on class A, B, and C. And with class A, B, and C, the class A is represented by the first bit being 0. What that gives us is the range for the first octet is anywhere from 0 to 127. So that gives us 128 networks that we have that are these giant networks that we would then assign these to these really big companies. companies or these really big organizations to represent large countries. And so this is the Class A range. For a number of hosts, we've got 16,777,216. Of course, I put a -2 on here because the first one is the network address and the last one is the broadcast address. So when it comes to actual nodes, we got to subtract 2 from that combination right there. So we can see that Class A's are really large networks, and we only have a few of them, 128, to be handed out. And in fact, a couple of those, I should put a -2 right there because a couple of those are actually already utilized for other things as well. So that's the Class A range right there. A Class B right there starts out with a 1-0. And when we figure that out, we actually have 128 to 191 range when it comes to the first octet. But we actually remember the network side of this is both the first octet and the second octet, which gives us a lot more networks. In fact, it gives us 16,384 networks that are broken apart in this Class B. And then for each one of those networks, we have 65,536 nodes. And then we subtract 2 from it once again because we've got that network address and that broadcast address. So that is a Class B right here. Then we have a Class C network. And a Class C network is 110 are the first 3 bits of that. That means that we have the range for the first octet is anywhere from 192 to 223. But keep in mind too with this is then we have the first, second, and third octet represents the network side of it. So we have a ton more networks that we can represent. Over 2 million networks in this right here for a Class B. And then for each one of those networks, we only have the possibility of 256 minus 2 nodes that are on there. So we only have 254 usable hosts on those networks. So this is the classful system, how the classful system's broken down, the different ranges of the first octet that we have represented in there, how many networks there are possible with those, and the nodes, the number of nodes that are possible with each one of those. Now, even the classful system was too restrictive. We still found that there's only 2 million networks, or a little over 2 million networks that can be assigned out there, and the network was growing. Lots of networks were popping up, and so we needed to address even more networks. We need to even grow and expand even more. And there's still those big, huge networks that had lots of different hosts that can go on those networks. So that's when subnetting came out. Subnetting was defined in 1985, and it was defined by RFC 950. And so that defined what subnetting was. Now, here I've got an example here of a Class C address, and I know that it's Class C because number one, the 192 falls into the range that is the Class C addresses. I also know because it starts with a 110. The first 3 bits there is 110, so I know that it's Class C. And so I know from this that from a classful standpoint, the first 3 octets is the network side of this. And so that gives us a lot of networks that we have to work with, over 2 million networks that we have to work with. And so then we've got 256 hosts that we have to work with. So now what subnetting is it allows us to, within the classful ranges, be able to subnet things out further. Let's say I don't need 256 host addresses out here. And so what I can do is I can further break that out. So if this address range was assigned to me, which is a 192.168.0, Then what I can do then is I can break this last part out into 2 different sections. I can add to the network side of this, and maybe I add another 4 bits, or what they call as borrowing 4 host bits to be the network side of this. And so what that will do is that will allow me, with my assigned range that I have right here, it'll allow me to break apart my network into 16 different networks, and it'll allow me to have 16 hosts. We do need to subtract the 2 from that, so actually 14 hosts. It'll be 14 hosts that I can put on each one of those networks. So I'll have 16 different networks with 14 hosts on each one of those networks. So that's subnetting. So that's defined by RFC 950, how I subnet a classful address into smaller networks. And then you can do that with each one of the classes. So you can do that with a Class A network that's given to you, a Class B network that's given to you, or a Class C network that's given to you. And that is subnetting. Then we have a few things that come out that define CIDR, VLSM, and classless routing. These come out all around the same time in 1995, and a couple of the RFCs that define some of this is 1817 and 1878. And what the problem is that even with the subnetting, we still start running out of subnetting space, and our needs are changing, our needs are growing. And so CIDR and VLSM, and classless routing, there's a lot that goes into that. And we're not going to talk about all of the little nuances and changes with this and what goes into this. But essentially, what we have now is variable length subnet masking, and we have some different notations or different ways that we can write this out, and different ways that routers will actually work. So with this, what I'm going to specifically talk about is variable length subnet masking. So before, in my last example, is we have a Class B right here, and then I gave the example of borrowing 4 bits so we can create 16 networks and then have 14 hosts on each one of those networks. And so what variable length subnet masking is it realizes that not all of your networks are going to be cut down into the same. So for instance, let's say one network I have has a lot more than 14 hosts, and so it needs to be a lot bigger. And then the next network that I have needs a lot less. Maybe there's only a couple addresses that are needed for one of those networks. And so what variable length subnet masking is within this network that was handed to me, 192.168.0, I can have a network that's divided where I just have 1 bit that represents the network and the rest represents the host for the first network. And the next one, perhaps I have a different network. So then I have different subnets all within this. So I can break this into a block of 128 hosts on the network, and the next block to have 64, and the next block could have 32. And so within this range that I'm given, I can actually have a variable length subnet mask, or VLSM, a variable length subnet mask. Now, the key to this, though, is that you can't have them overlap. You can't have 2 networks that end up overlapping each other. So I'm not going to get into the bits and all how we determine that. Once again, it's a topic for another class. But just know that in this iteration of this, in 1995, we can't come out with this way to variably subnet our networks, so that way we don't have these big blocks where we have to. All of the subnets are equally divided up. Instead, we can actually have it vary within those networks. Yet we still have issues. We still run out of network space. All those things that we have mentioned do help with it, but the needs of the internet is expanding rapidly, and somehow we need to adjust our IP version 4 ranges so it adjusts also. So we need another way to address the issue, and so that's where private addresses come from. Private addresses are defined in 1996, and it's defined by RFC 1918. And so RFC 1918 defines these ranges right here. So we have a 10.0.0.0, a 172.16.0.0, and a 192.168.0.0 as being private addresses. Now, one thing to note is that you can see that we have three options here. The three options that we have are in each of the different classes. So that way we can, if we have a really big network we can manage, then maybe we choose the 10 network. If we've got a smaller network that we manage, maybe we choose the 172 network. And if we have like a home or something really simple, we can do a 192 network. So we got different networks that we can represent within here. So that's one thing to note. Now, the idea behind this is a private address is something that you can have, you can set up anywhere, and as long as it doesn't get out to the internet. And so within your network, we're going to say that this is my home network right here, and this is my company's network. And so with each one of these, my home can use one of these addresses, these address ranges, to define that network. And my company can use one of the ranges as well to define that network. And once again, it's not routable out on the internet. So once it goes past my external router, it's going to need to be translated into something that's not a private address. It will need to be a public address at that point in time. But what this does is it saves us from having each one of these machines taking up an IP address just to get onto the internet. In the old way of doing things, every single one of these devices that are out here had to have a public address. Now, in the new way, and what a lot of networks do nowadays, is they have these private addresses. In fact, it's becoming so common, and most of the networks out there that are at least your home networks and a lot of business networks now all take up this private addressing space, that when I worked in schools that still had public addresses for each one of their machines, it was actually that wasn't the standard, and so it was harder to find information on how to manage some of those devices because of it. So private addresses are a way to maximize the use by allowing people to take any one of these networks here, assign it to their local networks, but then it gets translated out to the rest of the world into a public address. And it does that in a couple different ways, in which we'll talk about next. So one of the mechanisms that works out there is network address translation, or NAT. You may have heard of NAT before. You possibly have even used the term NAT before, but you probably have used it incorrectly. Where we reference a lot out there of what is being NAT is actually a little different. It's port address translation, or PAT. So just realize the difference between the two, and often we refer to NAT and it's actually not NAT. So what is NAT? Network address translation. We have these private addresses here on the back end. And the idea behind this, at least at one point in time, is that not all computers or devices are going to be talking out on the internet at the same time. You're only going to have a fraction of those devices that are going to talk out to the internet and out to the rest of the world. Now, that's no longer true, because a lot of devices now, as soon as they get onto their network, they start reaching out to, like let's say you have Windows starts reaching out to Microsoft and checking for updates and registering things, and there's all of this communication that's happening when there's a network time protocol when you start up your machine. And so it's no longer the case where you have just a fraction of your users that are are getting out to the internet, which is why we really don't use NAT as much anymore. But the idea is, once again, is that only a fraction of your devices is going to need to access the internet at any given time. And so what happens is whatever your external gateway is going to have some IP addresses that are assigned to it. And then as a computer accesses the internet or goes outside of its network, it's going to then take up one of these addresses and it's going to be translated. So that packet is going to have whatever private address is assigned to it is going to be replaced by the public address as it goes to the outside world. That way, when communication happens and the packet or the reply comes back, then what's going to happen is that packet knows how to get back to this router because it's a public address. That router or gateway is going to get that information and translate it back into that private address to get back to your machine. And so it's translating it as it goes out, as it comes back through. And so you have, in this scenario, you have a limited number of addresses that are assigned to it. And so you have a limited number of machines that can actually get to the outside world because you're translating it IP address for IP address. So think of this, the key to this one in NAT is it's translating IP address to IP address. It's a direct correlation, and so you're going to actually use up your resources until those machines stop communicating, and then that frees up that IP address for another machine to communicate. So that is network address translation. Then we have a port address translation. Now we haven't really got too much into ports, but essentially port is just a channel that can communicate, and we'll talk about channels later or sockets later. And so port address translation is really what most devices use nowadays. When we talk about NAT, it's actually port address translation. So the concept is still the same, that you have these private addresses back here within your network, but then as it goes out to the outside world, it gets translated into another address. So we have an IP, a single IP address that's assigned to this gateway right here. Our gateway is assigned 51.64.85.31. And so as this information goes out there, it goes out and gets translated from all of your machines back here to this single address as it goes out. Now, then the question is well, how does it know how it's going to get back to each one of those end devices? And that is through the port. So there's some sort of port that's assigned to it. So let's use an example of maybe 43,600, or possibly it's a lower number, maybe it's 2,800. Anyways, there's going to be some sort of port as it exits out this gateway, some sort of port that it replaces the port within there. So as communication goes out, that reply is going to come back, and it's going to come back to that port, and then it's going to get retranslated into the internal IP address and internal port, whatever port was used to initiate that communication. So it's really what you need to know for now is PAT is port address translation, and it translates it to a single IP address and uses ports to do the translation back and forth between our private addressing networks and our public assigned networks out there. So yet after all of those mechanisms that we put in place, we still have issues, and we still use IP version 4 to this day, but we've been implementing and trying to implement for quite a while IP version 6. IP version 6 was actually first defined in 1998 by RFC 2460, and there's been several iterations since then, but just to give you an understanding of the scope of IP version 6, IP version 4, we know there's 4 groups of 8 bits, so we have 4 octets, and so in total we have 32 bits that are represented in the IPv4 address. That's 10 to the 32nd. That equates to over 4.2 billion addresses, and we're running out of those addresses. So to address that, the idea was, well, let's implement IPv6. Let's make it so drastically larger that we couldn't possibly think about running out of addresses anytime soon. So with that, it actually is grouped into 4 groups of 4 bits times 8 of those. And it's interesting how IPv4 groups things up. It's a little bit different than the IPv4 address. But in essence, we have 128 bits. So that's 10 to the 128th power, giving us that number right there. Just a crazy number of how many possible IPv6 addresses that we have out there. So we will talk about IPv6 later and what those look like, but this is an IPv6 address. This is the space that it exists in. It's crazy. Now, there's also what we're going to have to talk about at some point in time is how do we deal with these 2 different systems? We have IPv4 that's implemented in a lot of networks still, and we have IPv6 that's implemented in many of their networks as well. How do we translate now between those? And there's some mechanisms that will help us communicate between those and translate between those. But for now, this is a little bit about the history and where we're at right now, trying to make the transition to IPv6 to give us much bigger address spaces. So there you have it. We talked about RFCs, and I talked about specific RFCs as we worked through the different years and different iterations as IPv4 grew and then IPv6 came out. We talked about some of those original networks or the first iterations of IP addresses and how that was very limiting to only 256 network possibilities. So we created the Classful system. Once again, we quickly ran out of that rendering enough networks for us, and so we started doing some subnetting to give us more networks. That worked for a while, for a good about 10 years, where we realized we still need to do something different. So we implemented CIDR, VLSM, and Classless routing, and so that changed things up to now we didn't have to have these predefined subnets, but instead now we can break things up very differently, and we can do some summaries, and we can do a lot of different stuff with it. So it opens things up. Still have an issue, so we opened up some private addresses, so that way private addressing means that you can just take up within your network, assign these private addresses, but then be translated to public addresses once it leaves your network. And then IPv6, the need for IPv6 and the addressing space of IPv6. Thanks again for watching my video. If you liked it, could you hit that like button?